All right, we're going to look at some example problems from section 2.5, 2.6. First one here is practice problem 2.9. I went ahead and drew the circuit. What we want to do is find an equivalent resistance. So we want one resistor that is the same, that would act the same in a circuit as all of these resistors here. So we need to determine what's in series, what's in parallel, so we can combine them. So if we look here, there's 3 different resistors connected right here. That means that we don't have series, and there's no resistors that share the same 2 nodes, so we don't have parallel. Let's start on this end. Typically, we want to start on the end over here like this, but that's just kind of a general rule. If I look here, these 2 exclusively share that node. These 2 exclusively share that node. That means the 3 of those are in series. So I can redraw this. I'm going to keep every resistor down here the same, not doing anything to these. Not touching my 3 or my 4. But I'm going to put all of these in series. So this resistor is now 4 plus 5 plus 3. Resistors in series, we just add them up for 12 ohms. So now I can do the next step. If I look here at the 12 and the 4, I now have these 2 in parallel. They're both sharing the same 2 nodes. It doesn't matter that there's other things connected at that node. It just matters that they share the same 2 nodes, and they do. So let's go ahead and put those 2 in parallel. So there's my 3, my 2, my 6, and my 1. And I have 12 in parallel with 4. We often write this like that, or 4 in parallel with 12. So that's 4 times 12 divided by 4 plus 12, or what is that? I guess I have it on my paper here. That would be a little bit easier. That's 3 ohms. Now I have the 3 in series with the 3. And the combination of those 2 is going to be in parallel with the 6. So let's do all of that in one step. Again, I haven't touched this 2 ohms yet. That's going to be my new resistor. Here's my 1. So I have 6 in parallel with these 2 in series. 3 plus 3. So I have 6 in parallel with 6. Anything in parallel with itself turns out to be half that value because you have 6 times 6 divided by 6 plus 6. So you have 36 over 12. So this, we would do this first. 6 in parallel with 6, that's equal to 3 ohms. And now I just have 3 resistors in series. So my equivalent resistance, my REQ, is 2 plus 3 plus 1, or 6 ohms. Well, that is our final answer there. Now switch markers for this next problem. That's equivalent resistance. Now the other problem we're going to look at is going to combine several different things that we've done so far. And this is practice problem 2.12. And it looks like this. We have resistor up here, resistor here, a voltage source, resistor, don't need to go quite down that far, and a resistor. And this is 40, this is 10, 15 volts, 6 ohms, and 12 ohms. Then they've defined an I1 here, a V1, this is getting tight, across that resistor, an I2 here, with a V2 across this resistor. We're asked to find V1, V2, I1, I2, and the power dissipated by the 12 and 40 ohm resistors. Well, let's first look at making an R equivalent, and then we'll find the current through that whole thing. Okay, a couple different ways to do this really, but we have to think about what techniques we have already and what ones we may not know yet. So if I look, these two resistors are in parallel. They share the same two nodes. And these two resistors are in parallel. They share the same two nodes. So I can redraw this circuit. That squeaking just drives me nuts. 15 volts. This will be 6 in parallel with 12. And this resistor will be 10 in parallel with 4. Now remember, things in parallel have the same voltage. So the voltage V1 that appears across here also appears across here because it's between these two nodes. So we still have voltage V1 right here. Same thing for voltage V2. These two are in parallel. So my voltage V2 is still right here across these two nodes. What I can't draw up here is current I1 and I2 because this current is through this 12 ohm resistor. It's not going to be the same, right? Because if I have I1 and it comes down here, at this point, it splits 3 different directions. So I1 does not exist in this circuit. We cannot draw I1 at this point. All right, but what could we do? Well, we need V1 and V2, so we could do voltage division. I have V1 equals, I need my 6 in parallel with 12, and that gives me 4. And 10 in parallel with 4 is going to give me 8. I need those. All right, so V1 will be 4 divided by 4 plus 8 times my source, 15. So I have 4 over 12 times 15, or I get a V1 of 5 volts. Is that right? 4 over 12, yeah, 1/3 of 15, so 5 volts. Didn't feel right for a reason. V2, again, this is voltage division. I have 8 ohms over 8 plus 4 times 15. So for V2, I get 10 volts. I have V1 and V2. Now to find I1 and I2, I have to go back to this circuit because again, I1 and I2 don't exist in this circuit. There's no such thing. So if I go back here, I now have V1. This V1 is the same as this V1. So I now have V1 and I know 12 ohms. So using Ohm's law, I can find my I1. Ohm's law, I can say V equal IR. That's Ohm's law, right? Basic definition. So my I1 is equal to V1, solving for I, over R, or 5 over 12, and that gives me, I don't want to write it as 0 point something. Remember, we want to use milli when we can. So that's 416.7 milliamps. I'm going to do the same technique to find I2. So I2 is going to be V2 divided by 40, or 10 over 40, or it's at 250 milliamps. So there's I1, I2, V1, and V2. We are also asked to find the power. Now we have the current and we have the voltage, so our power becomes very easy. So I want to use P equals VI. My power, we'll just say power 1, we'll call it this 12 one, will be V1 times I1. I trust you can plug those into a calculator and do some math. So you get 2.08 watts. And P2, again, V2 times I2. And if we did the math there, let's see, our V2 is 10, our I2 is 250 milli, so that gives us 2.5 watts. And that concludes Chapter 2.